All right, let's dive into one of the biggest, most mind-bending mysteries in the entire universe: black holes. Are they really just giant cosmic monsters vacuuming up everything that gets too close? Or could they be something much, much more? Maybe even the key to understanding reality itself? Let's get into it.
I mean, that's a pretty bold statement, right? But it really gets to the heart of why physicists are so obsessed with these things. They aren't just cosmic vacuum cleaners. You should think of them more like nature's ultimate laboratories, these incredible places where our best theories of the universe get pushed to their absolute breaking point. And it's right there, at that breaking point, where we might just see what's really going on underneath it all.
So, why a key? Well, because black holes are the ultimate cosmic battleground for physics. They are pretty much the only place in the universe where our two greatest, most successful theories about how nature works come crashing into each other.
So, in one corner, you've got Einstein's general relativity. It's beautiful, and it perfectly describes the massive gravity of a black hole as the smooth, elegant curve in space-time. But in the other corner, you have quantum theory, which is all about the weird, fuzzy, unpredictable world of tiny particles. The problem: right at the edge of a black hole, these two heavyweight champions are forced to describe the same turf, and their rulebooks just totally disagree. Finding a single theory that can unite them, what we call a theory of quantum gravity, is pretty much the holy grail of modern physics.
But to really get a grip on where we're going, we first need to look back at where this whole idea came from. And believe it or not, the concept of a black hole is actually way, way older than Einstein.
Yeah, this whole journey kicks off way back in the 1780s with a pretty simple but powerful idea based on good old Newtonian physics. Thinkers like John Michell and Pierre-Simon Laplace started imagining these things called dark stars. It wasn't until 1915, when Einstein completely rewrote the rules on gravity, that the modern picture started to take shape. And then, in 1965, the brilliant Roger Penrose proved that these things weren't just some weird theoretical quirk, they were an unavoidable consequence of gravity.
So that original idea, it all hinged on a concept you probably remember from science class: escape velocity. It's really simple. It's just the speed you need to go to break free from a planet's gravity and just keep on going, never to fall back.
To put that into perspective, to get off the surface of the Earth for good, you need to be traveling at about 8 miles per second. That's the kind of speed a rocket needs to hit to actually break free and head out into deep space.
Now take something with a lot more mass, like our sun. The escape velocity there jumps to an absolutely insane 400 miles per second. The rule is easy. More mass means stronger gravity, which means you need to go a whole lot faster to escape.
And this is the brilliant logical leap that Mitchell and Laplace made. They just thought, okay, what if you could pack so much mass into such a small space that its escape velocity was faster than the speed of light? Well, since nothing in the universe can travel faster than light, that would mean nothing could escape, not even light itself. The star would be completely and utterly dark.
Today, we call that boundary the event horizon. And here's the really weird thing to get your head around. It's not a physical surface. You wouldn't smash into it. In fact, you could cross it and not feel a thing. It's just the point of no return. Its importance isn't what happens to you right there, but the fact that once you're past it, you are cut off from the rest of the universe. Forever.
Okay, so we've got the boundary, the line you can't uncross. But what lies beyond it? What's going on at the very heart of a black hole? Well, that's where we find the biggest mystery of all, a place where our entire understanding of physics just completely falls apart.
This is the question that has seriously haunted physicists for a century. Once matter collapses past that event horizon, what happens to it? Where does it end up? And the answer that general relativity gives us is truly shocking.
The theory points to something called a gravitational singularity. Now, this isn't just a point that's really, really dense. This is a condition where things like density and the curvature of space-time literally become infinite. It's a place where space-time as we know it just stops existing. And all our laws of physics, they just stop working. They're useless there. And this quote just nails how bizarre this idea really is. See, inside a black hole, gravity warps space-time so much that space and time actually start to swap roles. The direction towards the center is no longer a direction in space you can choose to go. It becomes an unavoidable direction in time, your future. The singularity isn't a where, it's a when. For anything that falls in, it is quite literally the end of time. But the problems aren't just locked away in that hidden center. Thanks to the incredible work of Stephen Hawking, we know there's a huge, profound paradox playing out right at the edge of the black hole. at the event horizon itself. So, Hawking realized that if you apply the rules of quantum mechanics near an event horizon, black holes aren't completely black. They actually glow, ever so faintly. See, the empty vacuum of space is fizzing with pairs of particles that pop into and out of existence all the time. Now picture one of these pairs appearing right at the edge. One particle falls in, but its partner escapes out into space. That escaping particle takes a tiny bit of energy from the black hole with it. Over trillions upon trillions of years, this steady leak causes the black hole to slowly shrink, and eventually evaporate into nothing.
Okay, so this leads to a massive problem. If the black hole is gone, completely vanished, and all that's left is this faint glow, what happened to all the information about everything that ever fell into it? The star, the astronaut, the spaceship, where did it all go?
And this is the famous information paradox. You see, a fundamental rule of physics is that information can never, ever be destroyed. If I burn a book, in principle, you could collect every single particle of smoke and ash and piece together what the book said. The information is just scrambled, not lost. But a black hole seems to take that book, wait for an eternity, and then just radiate away as random heat, completely wiping out any trace of what was inside. That violates the fundamental laws of quantum mechanics. It just shouldn't happen.
So the struggle to solve this paradox is forcing physicists to ask some of the deepest questions you can possibly imagine. It's making us completely reconsider the true nature of space and time.
So how do we get out of this mess? Well, some of the newest theories of quantum gravity suggest that maybe those singularities, they don't even exist. Instead of a point of infinite density where physics just dies, maybe the center is a regular black hole, a core of extreme but finite density. In this scenario, space-time gets unbelievably warped, but it never actually breaks. The end of time gets averted.
But the implications of solving this go even deeper. The consensus that's starting to form among physicists is that for information to ever get out of a black hole, our very picture of space-time has to be wrong. Space and time, the very fabric of reality, they might not be fundamental at all.
This is the wild idea of emergent space-time. The theory goes that space-time, as we see it, is built from something much more basic, kind of like how the image on your TV screen is built from tiny pixels. And these fundamental pixels of reality, they might be connected by the spooky quantum link known as entanglement. The theory that describes this deeper level of reality is that holy grail we're searching for, a complete theory of quantum gravity.
And this is exactly why we study black holes. They are our ultimate probes, our best tools for trying to peer past the illusion of space-time. It's like Einstein said, if you're patient and you just keep pulling at these incredibly complex threads, you might just get to see a tiny piece of the deeply hidden structure of reality.
So, we end up right back where we started, but with a much, much deeper question. Black holes force us to face the possibility that our most basic assumptions about the universe, the existence of space, the flow of time, might just be a shadow of a much more profound underlying reality. And that's the ultimate takeaway. Black holes aren't just the end of time, they might just be the beginning of a whole new understanding of, well, everything.